Greenland, where he conducted the first detection of plasma lines at that line of longitude. He's been at Boston College since 1989, where he's been instrumental in locating imagers at various exotic sites around the world, including the Russian Arctic. He is now principal investigator of the first distributed observatory that is presently operating in South America, providing real-time observations of the ionosphere in a regional context. He conceived and led the installation of a network of GPS receivers, magnetometers, and ionosondes across the continent of South America. He's currently studying several space weather issues related to equatorial plasma bubbles and seeding conditions due to atmospheric gravity waves. So we're looking forward to hearing about details of how UNAVCO's infrastructure can support your studies. And take it away, Cesar.
Yeah. Thanks a lot, Freddy. I want to thank David and Glenn and also Linda for inviting me to give this talk to you. Just one small correction, I'm already using data from UNAVCO. Yeah, and you are going to see how it's helping me to do some discoveries. This is actually the first slide you could see the field of view, which I'm going to show later. This is the ionosome, which is a small radar. But these are huge antennas. These are 36 meters high, and they are separated by 75 meters. Next, this is the outline of my talk. I'm going to describe what's space weather. The space weather is like a new field in physics. It started about 15 to 20 years ago. We are many scientists working on this, colleagues. It's also like an umbrella. We can get some funding also from space weather. So I'm going to start from the very beginning. I hope I'm not going to bore you, but the beginning is at the sun. So I'm going to show you a movie. And then talk a little bit about this Carrington event that happened almost 2 centuries ago, but it could happen anytime. Actually, when we get close to solar maximum, there are more probabilities. Next year is going to be solar max. Well, and then there are all the issues also in space weather, things that come from below, and that's the things that Isaias and myself are studying, which is we call spread F, ESF here, or scintillations, and it has many names which I'm going to describe to you. And then a new idea that has emerged in the last few years is this distributed observatory, just to duplicate what other people in other fields are doing, like tropospheric weather and so on. And then I'm going to go to the new aspects of new discoveries that we are doing in the last few years, especially using the data from GPS receivers. And then talk about these TIDs, which means travel and ionospheric disturbance. And a term that I'm going to use a lot is this TEC, which means total electron content, which is just an integration, a linear integration of the density between your receiver and the satellite. And the satellite is 20,000 kilometers. But mainly comes from 300 kilometers altitude. That's where the ionosphere is. I want to stop this and then go to the movie. What you are going to see is when a coronal mass ejection leaves the sun and projects. This movie was made by NASA, and different satellites were taking pictures at different locations. So there is a SOHO satellite, for example, and this is the sun. Yeah, it's more or less at this. And from the corona, you have always is sending what is called the solar wind. The corona is the hottest part of the sun, and that's where the solar wind emerges. And this kind of cloud, which sort of attenuates as it gets to the Earth. Here is the Earth. I think this is another of the inner planets, but anyway, Mars or Venus. And then when it hits the Earth, this what is called here a coronal mass ejection. will produce what we call a magnetic storm. So you can show it again on the mass that is ejected from the sun is called the solar wind. And it's always there, actually. We always receive the solar wind. And the velocity is like 400 kilometers per second. The density is small. When it reaches here, it's about 1 particle per centimeter. But when we have these clouds, these coronal mass ejections, the density increases a factor of 100. The pressure, the magnetic pressure increases. This has also a magnetic field, which is gigantic sometimes. So the velocity increases also, and you have like 3 or 4 times the velocity. And of course, the time that it takes to leave the sun and reach the Earth is going to be much smaller. Instead of 2 days, could be just few hours. So when we have these coronal mass ejections, there is a lot of problems, which I'm going to show you here. Problems with the satellites, problems with the equipment, problems with the power lines also. So all these things are. So that's why space weather. This is one of the aspects of the space weather. So let's go back to the presentation. Probably you are asking how often we have this. Fortunately, it doesn't happen very often because the space is vast, and the Earth is just a small point. So this starts when you have a solar flare, and sometimes you have a combination of solar flares, and then they put together, and then we have this coronal mass ejection. Well, and then reaches the Earth, and then some part is going to penetrate. But we have this magnetic field around the Earth, which is protecting us. So there is no direct impact. But there are some processes when it reaches the shock. So the plasma that reaches tries to enter, but it cannot enter through the magnetic equator, say. The only way is through the poles. So there is part that reaches the Earth, through the poles. So particles that reaches, and that's what is called, electrons mainly and ions, and produce the auroras. So it's the particles that come from the solar wind. Something that I didn't end is when I was saying that these magnetic storms happen only 3 or 4 times a year. And usually they happen during solar maximum. That's when the more intense are. So in 2003 and 2004, we have several of them. They produce a lot of effects, and sometimes they have to turn off the satellites to avoid the impact of the particles. And also the magnetic pressure sort of makes this the point of contact, which is called the magnetic reconnection, makes to be closer to Earth. And then it could be so close, like 3 or 4 radius from the Earth. And there are a lot of satellites there, geostationary satellites. So that's the problems that we have. Fortunately for us, we can work on these topics. So we have all these particles, but there is not only particles, these electric fields, magnetic fields. But so it's a combination of mass, energy, and momentum that enters to the Earth. Here is the aurora oval that you can see. Usually it's like half the size of this, but this is during a magnetic storm, which is called the Bastille Day storm. When the oval grew to about a factor of 2, as I said, and you can see the aurora even in the United States. So that's why when you see the aurora in the United States, because it could be a magnetic storm, it could be also other phenomena that happen with it, but they are very small intensity. Of course, the Earth is rotating along this day side, is in this part, and midnight is about here for this day. But the electric fields that also get into the polar cap, into this region, produce the motion of the plasma. So most of the time there is like 2 cells, moving like this, the plasma. But when we have these magnetic storms, these convection cells grow also a lot, and they could see plasma from the United States moving. Like in this picture, here at the top you see is a part of the plasma that was at mid-latitudes over the United States. Due to this convection cell, it's moved into the polar cap. And that produces a problem, because you have gradients in the density. Now, who is worried about this? For example, if you are trying to land an airplane using a GPS, your GPS is going to detect the effect of the ionosphere. So for every 6 units of TEC is 1 meter that is going to be mistaken. So, and this can grow up to 100 TEC units. So there is an error there of 30, less than that, 16 meters that can be produced by that. But there is another effect which is even worse, is that here you have a structure, and those structures in the ionosphere are going to produce scintillations. And that's even worse because you won't have any signal coming from that satellite. I'm going to show you more about this in the other slides. So this is an event that happened in 1859. Of course, there were no satellites, there was no even power lines and all the stuff. But there was an astronomer who recorded this event, and his name was Carrington. So in September 2nd, 1859, the aurora was observed not only in the United States. So all these dots are the places where aurora arcs were observed in these locations. And they were observed even in Cuba. Even there were some sites in the northern part of South America. So this was a huge growth of the aurora over. So we have never had, after this time, something like of this magnitude. But that would be, with the technology that we have at this moment, that would be completely disaster for us. Well, as I said, there is this problem also with the power lines, and the reason is that these electric fields create current, and the currents induce a magnetic field, and the magnetic fields can go here, and these transformers can have an extra current due to this induced magnetic field, and this current may kind of destroy sometimes the magnetometer. So when this happens, the electrical companies know that they have to distribute the load in different ways. But there has been times that they didn't know this, in the early 90s, and they had some problems. So this is why space weather is important. It's the state of the sun, the solar wind, and also the complicated with the magnetosphere, but also the ionosphere. The ionosphere is the region that is closer to Earth, at 300 kilometers altitude. Now, somebody made an estimate. If we have a magnetic storm like the one in September 1859, probably the size of this corona mass ejection could produce a destruction of around $1 trillion or $2 trillion because of the destruction of the satellites that could be produced. Or many satellites have to be turned off to avoid the different kind of problems. Well, now I mentioned all these space weather issues coming from the sun, but there are other issues also coming from below, practically from the troposphere. Let me give you just a small description of what's the ionosphere. The ionosphere, the density in the ionosphere is in this way. It maximizes about 300 kilometers. It's produced by extreme ultraviolet radiation. So it's the sun also that produces, releases one electron. And then when the atom releases the electron, it becomes an ion and an electron. Of course, the charge is zero, because there are so many electrons as ions. But the ionosphere has benefits, but also is a problem for communications. when the ionosphere is smooth, the rays can go through that. There is nothing. But if there is any disturbance in the ionosphere, and that's when the distortion in the electromagnetic signals coming from the satellites get distorted. And sometimes they get eliminated. Well, it happens that sometimes you have these gravity waves going, even reaching the ionosphere at 200 or 300 kilometers, and can produce a small modulation in the bottom side, say here. And that modulation, combined with the gravity, will produce an electric field. And that electric field will make this disturbance to grow. So that's an instability that starts in that way. So it's the combination of gravity, the disturbance due to the gravity wave, or TID, and the electric fields that make the plasma move one part down and the other part up. So somebody make a very good schematic saying that it's like a bubble going from the bottom side all the way to the top side. And besides, if you look carefully here, this is a heavy fluid which is resting in a light fluid. So this is well unstable. So actually it should be all the time unstable, but it's not. So and that's another question, why is it not always unstable? Because you have always the heavy fluid over the light fluid. And the answer is the magnetic field. So the magnetic field sort of keeps everything in place. And the magnetic field also communicates any electric field to the other parts. So if there is an electric field, as I showed in the previous transparency, this electric field will go along the field line and then reaches the 100 kilometers, which is called the E region. And then it will sort of short circuit because the ions and the electrons can move freely there. But in the ionosphere, they go circulating around the magnetic field. So the E region at 100 kilometers, they sort of short out all these instabilities that grow. Okay, so good. So we don't have anything during the day. But during the night, there is no E region, and all these instabilities can be produced. So that's what I'm trying to study, and SciAS also studied this thing, how we can forecast these instabilities that happen. So this is different kind of observation of the bubbles that I was mentioned before. These instabilities that grow from the bottom side and reach the top side. So this is a satellite, for example, that went through those. And actually, there are several here. And you can see that more or less the size of these. These are 100, 200 kilometers in size. And here is the result from a radar. It's a coherent radar, which is placed in Jicamarca near the magnetic equator. And they look perpendicular to the magnetic field. And they receive echoes from 3 meters irregularity. So what happens is in these walls, you have other stabilities occurring, and they produce all kinds of structures. Starting from the 100 kilometers, they go down to 3 meters, even below that. So you have echoes from that, from these irregularities now. So you send a signal, you have an echo coming from these structures existing in the ionosphere. And you can see how high this bubble went, up to 1,600, 1,700 kilometers. So they go very high. So these bubbles really rises a lot. And they are also extended along the magnetic field. So these are the 3 dimensions of the plasma bubbles. And here, this is data from imagers. They were sort of south of the magnetic equator, and these lines represent depletions. Depletion due to these fight out, these holes, these bubbles there. And this is data from a GPS receiver. Here, it starts decreasing. It's because of these holes, because of the plasma bubbles. So this is the way that we detect this. Okay, now we have a plasma bubble there. And this, that we call GPS scintillations, it comes from the carrier to noise, which I was describing to Freddy before. We also, from the GPS scintillation, from the GPS receivers, we take also the carrier to noise, and we find the standard deviation of the variability of this carrier to noise, and divide by the mean. And this is what we call the S4 index, which is probably not here. The S4 index is a measure also of these plasma depletions. So that's why it's important to have this. And sometimes also we measure the same variability of the phase, because there is a good relationship between the amplitude and the phase. Of course, this TEC has been obtained combining the pseudo ranges and the phases from L1 and L2. Well, this is a schematic of what's happening. We have the signal coming from the satellite, and then there is a diffraction. It's like a diffraction pattern when it reaches a region that has a structure. So it needs to have a structure, and then it changes the angle. And then when it's traveling out of that, so from the ionosphere to the Earth, that's when they combine, and they produce what is called some kind of filtering. Well, some of these, because they have different phases, now when they get from this diffractive region, they will cancel out. And when they cancel out, what happens is that there is no signal now. When they cancel out, that means when they are exactly 180 degrees apart, they will subtract, and there is nothing coming to the ground. And then there is no signal. That's what we don't want. I think this plot was done for the militaries, and I think this is a soldier with a rifle, but any person with a GPS will have the same problem. He won't have that signal from that satellite. And that's illustrated here. Usually we have a good constellation. There is 30 or 31 satellites. So if you have your GPS receiver antenna here, the antenna will receive signals from these 6 satellites which are in space. If the signal from one is just crossing part of these bubbles, probably the signal won't be affected that much. But if it's transmitting like along the bubbles, so one is sort of aligned with the elevation of the satellite, so probably you won't have any signal coming from here and any signal coming from here. Usually what the GPS does in order to determine is he uses most of the time uses the satellites which are at lower elevation. But maybe we need a smarter receiver in order to know which ones could be contaminated because of the bubbles, which one don't have a good signal, and then go to another satellite, because it needs only 4 in order to determine the position and the time. This is something that was done by a colleague of mine, and he had a GPS receiver in one region where there was a lot of these disturbances, and he had a calculation of the position, and you can see that the error first is very small. This is the horizontal error in meters, so it was the order of 2 or 3 meters only. But suddenly, you have these disturbances. You have these holes in the ionosphere, these structures there, and then the error increases to 100 or 200 meters. So and this was calculated just with the same program that he always is used for. And you can see the effect, how the error increases. And this is for the vertical, and sometimes the vertical is more important to have than the horizontal, how the vertical position also is disturbed when you have these perturbations. Well, GPS receivers are used by many institutions even in cars or in trucks. So almost everybody is depending now on GPSs. One of the main users is the avionics, trying to land airplanes using GPS receivers. But this community realized to use a GPS in an airplane was not feasible, in the sense that they have all these problems about positioning, especially in countries like in South America or in Africa or in the Philippines. So what they did is they created an augmentation system, or something that augments, and there is a wide area augmentation system that has been developed. So the FAA is working on that. I have actually a working system, a WAP system in place in order to to try to help the airplanes to land. There are several colleagues of mine that work on that field in Boston College, trying to help the FAA determine how to increase the effectivity of the system. Well, I mentioned before about this when we have these disturbances, these plasma bubbles, these holes or bitouts, many names for the same, that they extend along the magnetic field lines. When you have a nice E region, well, okay, there is no going to be any disturbance because they will short out the electric field. So this is what he's saying. So based on this idea, we decided, okay, let's put some instruments here, and also at the center. And this is one of the reasons why we have this project, which we call LISN. So we are putting radar here and also at the feet of the field lines in order to know what's happening when this disturbance starts. Because not every night occurs. Sometimes occurs, sometimes doesn't occur. So this is just a generic picture of all the disturbance that we have. The ones I described are these plasma bubbles or holes, bitouts, are elongated like this. They happen usually at the magnetic equator, and they just slowly drift toward the east most of the time. But there are disturbances also in the polar cap. This is what is called the polar cap patches. So they are the ones that enter through midday and then start drifting here. So there's problems not only for the satellites satellite communication or for planes or for positioning, not only at the magnetic equator, but also in the polar caps. The mid-latitudes, which is the region where most of the people live, is the more benign environment where we don't have all these structures. Only when we have magnetic storms is when structures happen here. So it's sort of a summary of what all these effects of the space weather, that, for example, you have these solar flares, you can have energetic electrons or energetic protons that can affect the solar panel or can damage the electronics of the satellites, And you have sometimes currents, ionospheric currents, and this could affect also the power lines, or the transformers. So all these effects, are what we call a space weather effects, and also the landing of the airplanes, also which can be disturbed when we have all these density structures in the ionosphere. I have also another similar cartoon representation of the other space weather concerns or effects that we have. And for example, here we have the plasma bubbles, which I mentioned before. So we have a signal from the satellite coming to the ground. It's affected by here, and maybe we don't receive any signal. So NASA came out with a good definition of a space weather that says all the conditions on the sun, in the solar wind, magnetosphere, ionosphere, thermosphere, that can influence the performance and reliability of a spaceborne and ground-based technological systems, and can endanger human life or health. So that really goes through all 5 communities that work in our area. Well, this is a tropospheric weather view. And this was done not combining only view from the satellite. There is other instruments, that also are performing at this time. These other instruments, which probably are on the ground, they are able to measure the winds, how this system of rain or clouds are moving through the environment. This gave me the idea of trying to build another type of observatory. But I'm not the only person who has this idea about having a different type of observatory that we have used or we have had before. So this is a good way of trying to represent or study the weather the tropospheric weather, because you can see what's going on. But you need a satellite in order to see that, no? But you need also ground measurements in order to see where are the different levels of the pressure, no? What are the wind system that is moving at this time. Of course, you know that the weather people have also models that run at the same time with these images, no? So they can forecast also how the weather is going to be in a few hours or few days in advance. So based on that, there was a meeting a few years ago, and then this idea about DAISY came out. DAISY means a distributed array of small instruments. So why not to use small instruments like GPS receivers, or magnetometers, and put in different places and cover not only just one place, something that we have always done, but cover a region, cover a continent. So that was actually the idea that I have. I started with the idea of using GPS receivers and knowing that there were many already in place for other communities. So DAISY, also informed that the spatial distribution of ground-based measurements was not good for if we wanted to really solve some of the problems. And remember also another point, these plasma bubbles that we are trying to determine when they are produced and trying to forecast, they extend also in the north-south direction. So there was really a need to have these distributed observatories. Well, let's do a comparison with a local observatory, and the best example is Jicamarca, which is located near Lima. It's about 30 kilometers from Lima, and this is the big antenna. It's actually the biggest antenna in the world of this type. They are dipoles, and there are two antennas, one on top of the other. So it's kind of cross dipoles. But there is not only one radar. There is many radars, as you can see here. There are Digizone, and there is now a Viper here at the back, which is a different kind of ionosome. So there are several radars. And through the years, actually recently, new instrument has been placed in Jicamarca. This is two hills behind. This is the main antenna, I believe, is here. So there is an optical observatory, a Fabry-Perot. There is a camera also trying to detect how the winds move in the thermosphere, which is 100, 200 kilometers altitude. So several different studies that are done also. Now this is a list of instruments that we have not only at Jicamarca, but also near Lima. This is the incoherent scatter radar. This is a mesosphere stratosphere radar. This is a full radar, which is just a coherent radar, so very low power. There are Fabry-Perot magnetometers, and then there is LISN. Even that LISN is another distributed observatory, but it was put here as a part of Jicamarca. So this is what is the old type of observatory that we used to have, a cluster of instruments. So you have many instruments there in one place and try to study many different aspects of the ionosphere and atmosphere or thermosphere at that location. We started, I believe, with one GPS in this place, but then came the idea of LISN. LISN stands for the low-latitude ionospheric sensor network, and what we have right now is 47 GPS receivers. We have also 5 3-axis magnetometers, as it says here, and we have 2 Viper ionosomes. I mentioned before, the Viper ionosomes is a new type of ionosomes, which are small radars, and they can obtain the profile of the density in the ionosphere, but only the bottom side. And all of these are to study travel ionospheric disturbances and study the phenomenon spread F, which relates to the plasma bubbles. But when we sent the proposal to NSF, we we mentioned that we were going to nowcast, which means tell them in real time where we see these structures and where is the value of the density in real time. To do that, we needed to have the internet or some kind of communication to our server. So what we did is we look in different places. Some big cities, of course, it was possible to get internet. But in other small cities, we rely on phone lines or cellular communication. So we can use whatever, but whatever is available. No? There are several conditions for this network of this distributed observatory. Of course, it's going to be expandable. That's something that we want to have. No? Include all the instruments also, all the types of instruments. This is something that we are working now. Not low-cost imagers that can be tried to cover, no? or even much smaller radars. Now there are radars that work only with 10 watts. So we are trying also to include that as the part of the distributed observatory. But the main thing is that the cost. We wanted to make it inexpensive. Inexpensive means really like $5,000, $10,000, no more than that. No? Usually for a big observatory as the one at Jicamarca is in the millions of dollars. So we are trying to move away from the big observatories and try to go to the distributed observatories that can provide a new science, a new kind of experiments, a new kind of data. Point number 6 is also important in the sense that we are trying to forecast. But in order to forecast, we have to do a merging between the data and the models, but a model that has the physics of the ionosphere. So that's the thing that we're trying to do at this moment. I'm trying to merge these two models and the data and try to get the drivers of the ionosphere. Well, the drivers of the ionosphere is not only the sun, the UV radiation, it's also more important the winds and the electric fields that are set up. So these models will be able to extract those values, calculate in some way. And when this is calculated, we can predict, go into the future. Use the same drivers and then jump in the future 1 hour and see and predict and tell when this is going to happen or not. For example, the onset of these bubbles. This is the illustration of the 47 GPS receivers that we have deployed in South America. You can see that there are several countries, but we don't cover everything. But if we include all the receivers that have been used in different places, including also the UNAVCO receivers here, some of the coconut receivers are included here, we have a very good coverage for most of South America. There are places, of course, that they don't have that good coverage, but most of them in this part of the southern part is very well covered. I believe when we interpolate, we can fill all these spaces. Mexico, there are more GPSs which are not included here. Some of them are local networks, and they don't share the data, but we are trying to talk to the persons in Mexico to get the data. So we are not only going to South America, we are trying to also observe what's going in this region. This region is important to us because all these effects that are in the troposphere, they launch gravity waves. And these gravity waves, by two-step motion, they reach the ionosphere. And those gravity waves are the ones that are seeding the plasma bubbles. They travel a long distances, thousands of kilometers. So they can reach to really low latitudes, this region, these gravity waves, and maybe seed, and then this plasma bubble, this disturbance will grow. So that's why it's important. By doing this, we discover things. We are discovering other effects, other type of anomalies that we didn't know before. So let me go just fast in this part. You may think that the region of the Earth with the highest density will be the subsolar point, but actually that's not what is happening, because everything, all the distribution of the density around the globe is controlled by the magnetic field. No? And even it's more complicated than the magnetic field. It was in 1947 when it was realized, actually this is due to measurements during the war, that probably was in India, no? that the peak is not even at the magnetic equator, but always there are two bands, one to the north and one to the south of the magnetic equator. This is the line of the magnetic equator. And here I try to represent like a three-dimensional view of what's going on. The plasma moves up due to the electric fields that get developed. It's the wind that moves the plasma across the field lines, and the plasma, boom, it moves up here at the equator. And then when it moves up the field lines, it will go down just following gravity to both north and south. So this is what everything expects. Two bands, one to the north, one to the south. So, and this has been explained. Now, this offers also the possibility of using this data of TEC in real time to know what's the vertical velocity, to know what's the electric field, and what's the system of winds. So you see the same ionosphere that we can measure with a GPS. Now we don't need the big radars, but we have a distributed, we have all over South America, can provide also these drivers that we wanted to have. So this is very exciting, and this is happening just in the last few years. But the ionosphere is never friendly. Like always nature is more exciting than we can think of. So these are 3 consecutive days, and you can see that there are many things going on. Now there is not these 2 bands. There is only the northern part in the west part of South America, and there is the southern crest in the other part of South America. And here there is a big interruption. I don't know if the wind system changes here abruptly, and then you have this, just at the center of the South America it changes, and here it's more complicated, just one part on the north and the other, nothing else. Continues at the south. That was in 2008. We were using only data for South America, but in 2010 we changed it, and then we started including also the Central America. And now, just looking carefully, we discover other things, and this is what we are calling now the tropical anomaly. This is the equatorial anomaly, only the northern crest. And if you look to the symmetric latitude of this, there is nothing. But 20 degrees away, there is enhanced TEC. So this is not equatorial anomaly, and now we know what's producing that. It's another system of winds that exists, and combined with the inclination of the magnetic field, because the magnetic fields now, they are north-south as other parts of the world. Here they are inclined and tilted to the east, and here they are tilted to the west in this direction. So that inclination of the magnetic field, which is different in the west part and southern part of South America, creates these other anomalies in the distribution of density, and also the same for TEC. Here we are still trying to understand this. This is not aligned east-west, this is aligned north-south. So we don't know what's happening here. And here there is a nice anomaly, and there is the same tropical anomaly that is here. Combination of these 2 processes at the same time. Well, we decided not to include only GPS receivers, but also to have magnetometers, and this is the location of the magnetometers. Here at the magnetic equator, we have also a huge current going only 3 degrees wide, and this current of electrons produce an electric field, produce also a magnetic field, of course. And the magnetic field can be measured with 2 magnetometers, one at the magnetic equator and the other away from the magnetic equator, here. So these 2 baselines are actually complemented with 2 more other baselines, and when we combine this delta H value give us the electric field. So we have the measurement of the electric field at 4 points across South America. This is some studies about these electric fields. One is measured on the west part of South America, which is the one in blue, and this is the other measured at the center of South America. And you can see how the behavior of these electric fields is very different. So just in 1,500 kilometers, you see a huge difference in this behavior, as we have seen in the behavior of the TEC. So this is a sort of new results that we have done in the last few years. Of course, the TEC also follows that. This is the anomaly which I was referring before, but this is some kind of horseshoe. So the anomaly is sort of closing and getting smaller and smaller, in indication of the electric field is smaller and smaller at this location, as you can see in the data of the electric field. Well, and then we go to this part about the ionosomes. As I mentioned, these bubbles are sort of north-south aligned, so we decided to put many bypass ionosomes. We have placed only 3, one at Jicamarca, the initial observatory, one at the magnetic equator, one in Tupiza in Bolivia, and that's the first image that I show you. In about August, September, we are going to Tucumán, Argentina, and we are going to install the third Viper, and then we'll go to São Gabriel. These two are conjugate, and you can see that the E region from these two places, São Gabriel and Tupiza, map, if you follow the field lines, they reach more or less 300 kilometers. That's where the bubbles start. So we want to see what's happening at the feet of the field lines when this bubble is triggered. So, and that was going to provide us all this information. This is a better view of the field of view. You can see that the towers, you can see where the receiving antennas are, the feed to we have also, we construct a shelter. So this was an empty field. And if you're careful, there is a GPS receiver here, very close to this part, maybe it's outside the picture. There is a GPS receiver also belongs to my business. So he gave me the contacts in order to talk to the people in the Bolivian army. And through him and the Bolivian army, we were able to install this instrument. These are some results, and you can see this is Puerto Maldonado, the magnetic equator. This is the bottom side profile. This is versus altitude. This is what we are changing here is the frequency. So we transmit at different frequencies. And when the frequency is equal to the plasma frequency in the ionosphere, the signal gets back, it gets reflected. It's like a mirror there. So it reflects back, and then we receive the echo, and we measure, we are sampling continuously what this time delay, and from the time delay, we go to distance or altitude. This is nighttime. This is after midnight, actually. You have to subtract like 5 hours. And then the trace gets sort of disturbed. So it's not nice as it was before. And the reason is that there are some structures in the plasma. These bubbles start growing. So, and this is the other station, the one in Tupiza, the one that I showed the picture of the antenna field. You can see that it happens there. And it happens before. Probably it was a bubble that is moving through the structure here. Here, of course, we have more receiving antennas, and we can do interferometry. So we can know how these walls of the bubble are aligned, how they are tilted. We can even determine if these are an early bubble or a late bubble in the developing. Probably was a bubble that has already been developed and it's just moving into the field of view. So first went to Pisa and then moved a little bit, a small displacement in the field lines of these two places. So these are all the instruments that we have. These are mainly the GPS receiver. We are using Novatels in most of the cases. We have magnetometers, as I was saying, and these were built by engineers in the Jicamarca observatory. And this is the modules for the Viper. This is one of the dipole antennas. So these modules control the radar, and they're very easy to program, so we can do different experiments. So usually we run every 5 minutes, we get one of these density profiles, but we can run much faster. We can run every 12 seconds, even 6 seconds. This was an old picture of our server. We are changing the server. This was a blade-based server. but we are changing now in modular. Unfortunately, this was discontinued by Dell, so we don't have a way to get more of the blades, unfortunately. We have a web page, and you can see the data in real time. And these are ionosome profiles. You can go to this web address to get the ionosome, or you change this, go to magnetometer, or you write here GPS, and you get the displays of the different GPS receivers. So all of this is freely available, but it's better if you write to me or one of the engineers in Jicamarca, and you get your password, and then you can download the data, not only see the images. Hopefully I have 5 minutes, and I can give you some. This is data from, this is the numbers that we are getting from all GPS receivers. This is only 30 minutes. You can see, this is for 2010. This is very strange to us. This is the afternoon time. Here it used to track like 6 or 7 hours. What you can see that the highest TC value was in Central America, not close to the equator, but far away from the equator. What we do is just an interpolation in order to fill the spaces. So the algorithm works pretty well, almost always. And you can see that this high TC value, this was very strange, very unexpected. And it finished abruptly when the magnetic field declination changes from being eastward to 0. This is close to the June solstice, and we can see that it happens sometimes, not every day, but it was like 25% of the time. This is one of the pictures I showed before, and now in the December, well, very close to the December solstice, you see in the other side, and only lasts for a few hours, and this is what I mentioned before, the tropical latitude, the tropical anomaly. So we have an idea what's producing that. We have models that have duplicated the data. This is another phenomenon that we are studying. This is what the gravity wave produces on the traces. I showed you before the traces that they look like single lines, and that's what we have during the day. But if there is a gravity wave, that modulates the bottom side. So, and the field of view of these ionosomes is large. It's like 40 degrees. So we cover a bigger space, but this bottom side is modulated. So we get here echoes from one side, which is higher density, and the other side, which is a smaller density. So in average, we have a trace that look like a letter C. So that's an indication that we have a gravity wave. At that time, we see what was going on in the TEC value. This is TEC values from Tupisa. Instead of being very smooth, like they usually are in other parts of the day, for example, here it's a smooth trace, we have a lot of wiggles there. These wiggles are due to the gravity waves, or also called TIDs, that are moving. So, and we are using these wiggles, and we detain the data in order to study the wiggles of the TIDs, actually, and to study the gravity waves. So we did an experiment near Huancayo, which is just 200 kilometers from Lima, and we put 2 additional GPS receivers in order to study the effect of the motion of the TIDs. So we obtained this variability. You see, this is only 2 hours, and usually the trace should be continuous. But it's not. It has this ondulation. This ondulation, which here is huge. And this is one of the PRNs. One of the satellites. The 3 traces means of different colors means different GPS receivers, and I had these 3 separated only by 5 kilometers. But we can use also GPS from different locations, even if they are hundreds of kilometers. And these TIDs, as I said, or gravity waves, they travel like 1,000 kilometers. So we do a cross-correlation analysis, and we can get the timing, the difference in time between when the gravity wave arrives in one location and the other. So based on that, we know what's the velocity and angle of arrival of these TIDs, and this is what we are doing. So these are the velocities obtained by 2 different methods, using the small array and using the LISN array. Now, as I mentioned before, I think when we have one of these bubbles and there is a GPS crossing, above that is going to see a sort of a depletion. And this is what we call TEC depletion. This depletion of byte out, of course, happens at the same time that we have scintillation. So these are TEC depletions. These are bubbles detected by the GPS receivers. But because there are more than 200 GPS receivers in South America, we can do a map of the TEC depletions, and this involves all the TEC depletions that were observed on this night, at these different times. So on this day, it was in one side of South America, and it was in the other side. But this scheme is very variable, and this is something that we discovered that why it's so variable. For example, these are 3 consecutive seasons. Usually we believe that it was a seasonal dependence, but depending on the season, we were going to have in one side or the other side. And there were some theories about that. And we only did measurements in several points in the continent. But now we have opportunity to do measurements all over the continent. And we discovered that, and the other thing, every day we can do the measurements. And then we discovered that sometimes these are consecutive days. It's everywhere in the continent. And the next day is just one part. And then the following day is the other part of the continent. So it's more random, apparently random, than we thought before. So just let me conclude with a summary. The LISN observatory provides continuous measurements, scintillations, and TEC depletions. This is the most important part for us. Isaiah works a lot in this scintillation part. And we are all trying to forecast this phenomenon because it affects the communications. And this is one aspect. And this is why we get funding from NSF, NASA, or in the past from the Air Force. We are also providing these regional maps of total electron content. We provide also regional maps of the TIDs, which I haven't showed here. And then, of course, this regional map of scintillation and TEC depletions. And the future efforts are all to trying to forecast the initiation of these equatorial plasma bubbles. So this is a very important part for us. The way that we are going to do it, I think I mentioned a little bit of that, is a physics-based assimilation model game, and there is different models that we use. So what it uses is the TC values from the GPS receiver. In order to do the forecast, we need this data in real time. Practically any GPS receiver in South America and Central America is useful for us. It will help us to do this forecast. We are also, of course, including the bottom side density profile that we measure with the ionosphere and the magnetometer. So this is all. Thank you very much for the attention.
So I have a question I'd like to ask. There's been a lot of work done correlating TEC disturbances with great earthquakes, specifically the great earthquake in Japan. I was reminded by this by your slide of South America that showed a disturbance that was within a couple of weeks of the large Chile earthquake. I'm sure that's just a coincidence, but that's what reminded me of it. And just wanted to get your opinion on where you stand on earthquakes causing disturbances in the ionosphere.
Yes. I know the correct person to ask because I don't think very well about those efforts. I have colleagues who are working on that. I can mention names, Wes Schwartz, Mike Kelly from Cornell. I have also. There are also some of your colleagues that are working on effects produced by the earthquake after the earthquake, like tsunamis. Tsunamis and the motion of the tsunamis can be detected by. Tsunami also produces like a gravity wave. So, and we can follow the gravity waves with these GPR receivers. So the afterward effect, yes. Yeah, we can do, and there are
precursors. No.
Yeah, precursors. I still skeptic about this effort. Yeah, and the main reason is there was this Russian guy, Polines. Once I was discussing with him, and he told me that for this earthquake, the effect came like 5 days before. For this other earthquake, the effect came 3 days before. You know? And then he was saying that he saw in his data some wiggles. You know? Well, it's really effect from the earthquake or the electric fields that grow from there, or it's just other type of thing like perturbation, gravity waves, TIDs. So,
right, just like what you showed happened 2 weeks after the Chile earthquake, likely had nothing to do with it. But
yes, yes. But it's sort of an irony that I gave a lot of data from Universidad de Concepción, I believe, to westward, and west discovered other kind of wiggles that are always there. You know? And then we are still trying to explain why these wiggles are always there, which are nothing to do with the earthquake. We believe at the beginning we saw there were some kind of mountain waves, which are produced. No, it's just the wind. No, and you have the mountains, and these effects go up to the mesosphere, 80, 90 kilometers. But they have never been observed in the ionosphere. I mean, 200 kilometers. So it's still a puzzle how these waves, mountain waves produced by the wind in the troposphere can reach up to 250 kilometers. So instead, we discover other things which are more in our field. I also believe that aeronomers shouldn't be the field of the seismologists. I really believe that. I mean, I know the seismology, they always tell me that they have used any kind of instrument that is available to measure the effects of the earthquakes.
So with the solar maximum coming again, I'm curious about whether or not there's been an increase or a decrease in the magnitude of the effects over the maximum. So when we started GPS working these observations maybe 2 cycles back,
yeah,
it would cause large problems because the instrumentation wasn't as good and you'd lose lock and all this. But was part of it because it was more extreme in those days, or how is the relative strength of these?
Yes, in some way you are correct. They were a little more extreme. No, if you see the peak of the solar max is sort of decreasing. No, it has been decreasing. I think that this one is going to be like 80% of the previous peak. No, there's some speculations, which may be true. There was sort of a decrease, but it seems that there's going to be a peak at next year, 2014. But it's going to be smaller than the previous one. And the previous was smaller, I believe, than the other one, or more or less the same magnitude. So, but it's just this effect of the sun that is behaving that way. There are some predictions that the next solar cycle will be even smaller. Some speculations about that, which is in some way bad for us. Yeah, in terms of funding, because there is nothing to complain about. I mean, the person who won't complain for this.
I have 2 questions. One is about the solar, the plasma bubbles.
Yes.
If I understood correctly, you said that they were stretched out north to south?
Yes, yes.
What's the physical reason for that? What's the mechanism that stretches them?
Yeah, plasma can travel along the field lines very easily, but across the field lines it's difficult. Yeah? So anything that happens, at one location stretches out north and south. It follows that. So you have a hole that is produced probably near the magnetic equator, and then you will try to have the same density along the field line. So if you have a small difference in the density, there is going to be some kind of electric field trying to maintain it the same. And that will move the plasma. And along the field line, as I said, it moves very fast. But across, it moves very slow. So they always like that, stretch it along the field line. And they grow also. So that's the three-dimensional picture of how they look like.
Okay, and I have a second question. It has to do with these variations that you see from day to day, which are quite dramatic.
Yes.
And I wasn't expecting to see something like that. Have you tried to correlate those daily dramatic changes with the solar observatory information from SOHO or Stereo A and B and other sources?
Yeah.
I mean, we have quite a fleet out there right now.
Yes. Yeah, stereo. Yeah. No, I haven't tried to do that. It's a good idea. I don't know how there may be some influences there. But of course, there is also the influence of the magnetic field, no?
Yeah.
The variations in magnetic field.
More technical question, probably. The ionosons, how do they work? Do you send a pulse with multiple frequencies and look at dispersion, or how does that? I have no experience with that. So.
Yeah, well, it has been an evolution through the probably 70, 80 years. The initial ionosons, it was just a generator, to create a sinusoid, like a continuous wave. And then they just changed the frequency. They are very simple instruments in some ways. And they were used during the war, World War II, a lot, to see just the airplanes, where they were coming, And they were simple radars, just sending an electromagnetic signal, having the echo, not from the airplane, but the echo from the ionosphere. They knew these things. These ones that we use are more sophisticated. Sometimes, of course, they always send a pulse. It's a pulse, but inside you have a frequency, that goes from 1 megahertz. And these are Tonko receivers, which are made in Australia. These Tonko receivers, you can just send a signal, and they will give you the frequency that you want. You specify what frequency you want, and then it will give you that frequency. And then it's low power, it's 3 kilowatts. And yeah, for us it's low power. Yeah. And then it will it sends the signal through the big antenna. And the bigger the antenna you have, you can observe a smaller wavelength, or smaller wavelength, or a smaller frequency, bigger wavelength, actually. So we want to go to very small frequencies, like 1 megahertz or half a megahertz, so we can observe smaller densities. In the E region, during the nighttime, the density becomes very small, and that's why we need big antennas. So that one was 75 meters, with a lot of gain. So, and then you send these poles, and you wait for the echo, and then you have these receivers. Now, in this area of the digital receiver, it's very simple now. So we have these, like the receivers in the cellular phones. We have this kind of receivers. Everything is digital, and it goes directly to the computer. And then the computer, we have 2 computers there, and it's analyzed and store, and then different kind of formats. We have 8 receiving antennas, and that's the thing. We do interferometry, so we know these plasma tilts, and so I have it shown here, all the velocities. So it's sort of sophisticated now. But everything can go just in one small rack. Maybe in the future we'll go just in one computer. So we are limited by the speed of the computer. So if the computers are in the future like 15 gigahertz, and then they should be able to go directly from the receiver directly to the computer.
What's the power consumption then of the big antenna you were showing? When power, like how much watts do you?
Yeah, no, it's limited by transmitter up to.
No, the big antenna array.
Oh, yeah, the one at Jicamarca.
Yeah, what's the?
4 megawatts. 4 megawatts. Yeah, but that's a different principle. It's no reflection. It's a scattering from the earth and the ions. So the principle of that instrument is completely different.
Any other questions? Okay, let's thank Cesar one more time.